Welcome to our strategic overview of aviation technology, tracing the arc from early propellers to the promise of autonomy. In this presentation, we'll explore historical foundations in propulsion and aerodynamics, current advances in materials and digital systems, and emerging frontiers like AI and sustainable flight, all framed to show how the industry is evolving towards safer, cleaner, and more efficient air travel. This slide shows the digital revolution that moved aircraft from heavy mechanical linkages to electronic fly-by-wire controls. That shift brought lighter systems, digital processing, and far greater control precision, while also introducing rigorous redundancy and safety architectures that paved the way for envelope protection, auto-land features, and the long-term path toward autonomous flight. Here we trace engine evolution from thirsty low-bypass jets to today's ultra-efficient high-bypass and geared turbofans, which cut fuel burn by roughly 20%. Looking ahead, next-generation open-rotor and hybrid designs promise further savings and noise reductions, while strict noise and safety regulations will shape how those concepts are refined and adopted in commercial service. Materials and manufacturing breakthroughs are reshaping aircraft design, from carbon fiber wings that reduce weight by around 20% to 3D-printed titanium brackets that slash lead times and enable complex geometries. Ceramic matrix composites are pushing turbine temperatures higher for better efficiency. And together, these innovations deliver stronger, lighter, and faster-to-market components that improve fuel performance and operational economics. Avionics have transitioned from clusters of analog dials to integrated digital suites that enhance situational awareness and reduce pilot workload. Combined with GPS, ADS-B, and advanced flight management systems, modern avionics enable real-time traffic awareness, four-dimensional trajectory optimization, and predictive fuel planning, creating safer airspace and more efficient routings for airlines and air traffic managers alike. Autonomous landing systems are advancing through redundant autopilot architectures and passenger-activated emergency autoland features. These technologies demonstrate reliable zero-visibility landings and automated guidance to the nearest safe airport, but full passenger autonomy still faces tough certification hurdles, extensive testing requirements, and the need to build strong regulatory and public trust before wide adoption. This comparison outlines three sustainable pathways: sustainable aviation fuels, cryogenic hydrogen, and regional electric aircraft. Each offers trade-offs in CO2 reduction, energy density, and infrastructure needs, with SAF delivering near-term emissions cuts, hydrogen requiring new fuel systems and certification, and electric aircraft suited to short routes pending charging networks and regulatory frameworks for broader adoption. Advanced aerodynamic efficiency focuses on drag reduction through blended winglets, natural laminar flow wings, and active boundary layer suction. These approaches reduce induced drag, extend laminar flow to cut skin friction, and remove low-energy turbulence for measurable fuel savings, though they bring integration challenges such as contamination, sensitivity, structural retrofit complexity, and maintenance considerations that must be managed. The eVTOL Air Taxi Roadmap maps technical foundations in the mid-2020s to network and regulatory milestones by 2030. Early phases emphasize distributed electric propulsion, noise limits, and cruising performance, followed by vertiport networks and U-space traffic management to scale operations, ultimately targeting certified regulatory approvals and for-passenger commercial services as infrastructure and rules mature. Autonomy and logistics integration cover feeder, fixed-wing UAVs for cargo, BVLOS operations supported by detect and avoid radar, and blockchain-based unmanned traffic management to safely scale high-density drone activity. Together, these systems unlock significant cost savings and enable applications like last-mile medical deliveries, while ensuring deconflicted airspace and reliable links between distributed hubs and urban logistics networks. Predictive maintenance leverages real-time sensor inputs such as engine vibration, bleed air pressure, and flight control pulses, feeding onboard neural networks for minutes-ahead anomaly detection. The outcome is a move from reactive to proactive fleet health management, with predictive logs that can cut unscheduled removals by around 30% and materially raise aircraft availability and operational resilience. The AI and Autonomy roadmap outlines a phased approach from simulated learning to phased passenger operations. Initial stages focus on machine learning from millions of simulated flights and control optimization, then on explainable AI to satisfy regulators, and finally on stage deployment, starting with single-pilot cargo operations and moving toward full passenger autonomy by the mid-2030 seconds as safety, transparency, and certification progress.